Can you see that?
Yep, that works. Perfect. Yep, so as I mentioned, Nick's a PhD student, primarily based at Newcastle, but as you can see from his opening slide, he's spent a significant part of his PhD also working in Trento. And today's going to be talking about the spin-up of the superfluid vortex lattice that's driven by rough boundaries. So Nick, please take it away when you're ready.
Thanks, Andrew. So yeah, I'm a PhD student on a co-tutel arrangement. So I just got back from Italy, which is where I did this work, but I did it with Newcastle collaborators, so it's a bit of both. So I'm going to be talking about the spin-up of a superfluid in a rotating rough potential. I'm just going to have a very quick introduction to VCs. I know most of you know more than I do. And then we're going to move on to the results I found. So first, I'll just go on the same page. What is a Bose-Einstein condensate? So you can think of these as big gas of bosons. As you cool them, they start to have some wavelength associated to their position. And the cooler you get, the largest wavelength gets. And eventually you hit some critical point where these wavelengths start to overlap and you generate this Bose-Einstein condensate. You push it even further and you go to like the lowest temperature you can get to, absolute zero. Then all these wavelengths overlap in such a way where it's a complete overlap and you have just a pure giant matter wave known as the Bose-Einstein condensate. The work I'm doing today is going to sort of focus in this picture where we're at the t equals 0 limit. We're going to do that using...
Sorry to interrupt, Nick. Well, it may just be me, but I'm still on your title slide.
I thought there was something weird. Let me try doing it again. How's this?
Yeah, perfect.
Okay, sorry about that. So yeah, I was just talking about, so you have this box of particles, they're bouncing around, you cool them, the wavelengths get bigger, and then they overlap until you get this giant matter wave, which is your BEC. So an interesting thing about BECs is that they facilitate quantum vortices. So on the right here is just a picture of one in 2D. It's a topological defect associated with a 2 pi phase slip. This is the phase profile here. In 3D, these things are like filaments, big long strings or cylinders. And what we're going to be looking at in this work is how these interact in a rotating rough bucket in a 3D system. It's important to note here that these are topologically protected. And so they can either, they must be generated at a boundary or they must come into effect in a pair event or through fluctuations. So we know that the stationary solution or the equilibrium solution of a superfluid is just this uniform solution where it decays at the boundary over some small heating length, and in the rest of the bulk it's just some solid value. And we also know that under rotation, you generate a vortex lattice. But what's been currently unexplored is the dynamics between getting from this equilibrium solution to the vortex lattice solution. So the system, when you put it under rotation, it wants to minimize its free energy. And the way you can do that is by allowing vortices to come into the bulk and align themselves in this vortex lattice here. This Packard group was the first one to actually realize this, and they did this using superfluid helium. And so there's two ways you can think of how these vortices get there, because you start with a still fluid and there's nothing there, and you get to the end point where you have this vortex lattice. So there's two schools of thought on that. So the first one is that, say you have a remnant vortex. We'll talk more about these later. So a vortex that's already in there, and under the right conditions, if you spool it up, this thing can seed the rest of the vortices, which form into the lattice. Another one is that the vorticity can enter through the roughness in the boundary walls, and that these rough boundary walls might facilitate the generation of vorticity, but that's exactly what we see in the rest of this paper. So the model we're using is the Gross-Vitesse equation. I'm sure you're all very familiar. The term of interest here is this omega Lz psi, which acts as the angular momentum operator. And by using this, we can rotate our frame of reference around the z-axis at some rate given by this capital omega here. So we introduce some quantities here so that we can rescale and have a dimensionless equation to simulate. So these are the sort of the uniform condensate wave function. So this is what should be in the bulk. We introduced the heating length, which I mentioned earlier, which is the distance over which this density will decay to zero at the boundary's edge or within a vortex. And then you have some natural time, which is the characteristic time scale that things will happen in the fluid. So we end up with this equation here on the bottom. You might have noticed we've also introduced this gamma term here on the left-hand side. And what this does, it's a phenomenological dissipation parameter that allows us to model sort of the dissipation of energy from our system. And so in real life experiment world, you might say this is by coupling to the normal fluid that it's encased within, but just acts as a numerical way of speeding up some of our simulations and the dynamics we see in it. I will say that we did test without gamma, and the results we saw are exactly the same. All it does is accelerate the findings that we get, because when you're doing numerics, you want to sort of speed them up as much as you can without affecting the behavior. So moving on to the rough bucket. So what we're going to do is generate this nice rough bucket to approximate what they might do when they're machining these real buckets for the actual liquid helium experiments. And what you get when you machine parts like this is you get some noise, some roughness on the surface, and that noise is usually characterized by fractional Brownian noise. So if you look at this top right figure here, this is that noise that we input onto the cylinder. You'll notice if you look down the phi 0 line, there's a symmetry here. So what we did is we just mirrored it onto both sides so that when you connect it up, the ends meet perfectly and you have no hole in your bucket where the fluid can leak through. So you have this fluid here. I'm not showing the top and bottom plates, but these are just smooth plates that connect them and stop any leaking of the fluid out from the top or bottom. So it's just two flat plates on the top, and then a rough cylinder goes along the edge. So these are some default parameters we use for our simulations. We're about to change some of these, so just before I introduce them first, before we start doing some parameter sweeps. So a typical bucket radius we do is 50 helium amps. The bucket height is 100 helium amps. We introduce a small dissipation value, and then we sort of engineer the translational speed of a feature on the rough boundary to sort of go across the fluid at speed c. Some studies into superfluid boundary layers, numerically that is, found that you can get nucleation of vortices at speeds of about 0.4 c. So this is way well above the value we need to generate vortice E, and high enough so that when we do generate the vortice E, the vortices can reach into the bulk and form the vortex lattice that we're looking for. So I think the best way to do this is I'll just show you what happens in the simulation, and then we'll talk about sort of the subtleties that go on behind the background. So in this yellow isosurface here is the confining potential. And when I press play, you'll see positive vortices in red, determined by the circulation, and the negative ones in blue. So I just play this here. You'll see that initially you start to generate these U-shaped or handlebar vortices that come out from the side, by sort of the relative difference between the fluid velocity and the moving boundary. These start to grow and interact, importantly, until slowly these vortices grow in size and magnitude to the point where they form these big vortex lines that sweep the whole box and start to reach the top and bottom. Once they do, they quickly push into the bulk and they form themselves into the vortex lattice they're expecting. And so the main purpose of this work is to study those dynamics as the nucleation event happens on the edge, how these things form into the boundary typically in the end. And you see at the end here, they're all lined up into the famous vortex lattice solution that we're looking for. There we go. So we wanted to look first at the angular momentum transfer. How does this angular momentum enter into the system? So you look at this top plot here on the right. So the ordering goes, let's move this, orange, green, blue, purple, and you see in time how this system evolves. So you see at the start, the angular momentum is focused on the boundary as you start to inject it from the boundary. Over time, this angular momentum creeps into the system, facilitated by these vortex lines, until eventually it forms up into these nice bands. So these bands are what we saw in the previous figure, where all the vortices have lined up into these sort of radial discs, accretion discs of vortices. So you can see one here. Here's the vortex line density corresponding to it on the bottom spot here. So you see that this starts to approximate the solid body rotation result for angular momentum as you get to the late times. And for a bigger system, we can't reach giant systems here because we're doing 3D modeling, but we've checked in 2D that you get approximately the solid body result. So the next thing we want to see, what are the effects of changing A, the rotation, and B, the roughness of this bucket? So if you look at the top line here, as you start to increase the rotation given by this omega value here, you start to facilitate more and more vorticity to enter into the system as this relative difference in velocity of the fluid versus the potential grows larger. This injection of vorticity sort of reaches a saturation point where you can only sort of hold so many vortices within your system, and spinning any faster won't really give you any more. And you'll notice there's sort of some centrifugal effects, just the same as you would in solid body or in classical fluids, as the density sort of gets swapped into the edges as you spin faster and faster. On the bottom here, we see what happens if we try and vary this roughness parameter A. So you can sort of characterize the noise profile by the average radius of curvature on the surface. So if you look here, this one has a value of 5.2. If you make the radius of curvature larger, you're creating a smoother potential. And as you make this thing smaller, you're making a rougher potential. So as you, there's actually a result here, and I'll talk more about the next page, but if you compare the intervortex spacing distance, so the typical distance between vortices, and this radius of curvature, if this is large compared to that, then you get a vortex-free region around the disk. So you'll see there's a band here around the edge, more clear here where you have this larger radius of curvature, where you could fit an extra band of vortices, but they don't appear. And this is a predicted result. It hasn't been found before. It's been predicted back in the 70s, but no one's really done a numerical simulation to validate. And this is the first evidence we see of it. As you increase this A parameter and therefore increase the roughness with it, you start to encroach more and more into the fluid space. And you get to a point where your boundary encroaches so much on the fluid, you actually restrict the development of vortices in that edge zone, and you minimize the vorticity in your system because you're leaving it less room to develop the vorticity within. Looking next. So then we want to check, what does the radial velocity profile look like? So if you just average azimuthally and look at the radial velocity profile, you'll see for the small values, it approximates fairly well the solid body rotation result that's expected for quantum fluids. But as you spin this thing a bit quicker and you allow more and more vortices to enter your system, you get a much closer approximation to the solid body rotation result. You'll notice it is some oscillation because you have these bands of vortices which are contributing to this velocity profile. It's not like the continuum you'd expect in a classical fluid. And as I said, you get this vortex-free region as predicted by some of these papers back in the 70s. Moving on. So another thing we wanted to look at was how does the vortex line length evolve? So we have some algorithm that tracks the 3D vortex filaments in space. And we know at the end, we're going to have this vortex lattice profile where all the vortices are lined up along the Z axis. So we know the time, the total vortex length in our system is going to be the height of our potential times the number of vortices that we have within it. If you project this length along the XY plane, you'll know that in the end, again, that should go to 0 because they're all aligned axially. And again, this, if you project it to the Z plane, you just recover this total vortex line length lambda. So these are plotted here. And so if you look on this bottom left graph, the solid line is the total vortex length. The XY is this dot dashed one, and projected in the Z is just the dashed one. So you see for the regular case, you have this evolution and the vortex line length saturates when these things sort of reach the bulk, and then they slowly sort of move around to find the lowest energy state, as you see here. As you start to increase this velocity, more and more vorticity enters your system. And as I said before, you sort of saturate a point where, although this vorticity entered like stronger here, there's no room for it to live within a system. So this decays. Vortex rings are formed and these decay, allowing you to sort of remove some vorticity from your system. Looking back to the roughness here, so you see that for the typical roughness, you generate in sort of call this the default one. As you halve it, you'll see that the roughness is less, and so it takes a longer time for vortices to be nucleated at the boundary, leading to a slower injection of vorticity into the system. So you have a slower injection rate, as you can see by sort of the right shiftness of this red line here. And if you go to the other extreme, where you look at the very rough case, you have this big initial input of vorticity, but it actually leads to a lower total vortex count, because you're sort of leaving less room for the vortices to live within as you increase the amplitude of this roughness. We also wanted to check, so in these experiments, what would happen if you had some dodgy machine and you created some little bump in the surface? How would this affect the results? In an experiment, could you notice if there happened to be some protuberance that sort of stuck out? So we modeled this. You can sort of see it in the back right corner of this video here, and you'll see, when I press play, that this creates some sort of anisotropic vorticity profile at early times, as these these isotopes sort of emitted from this barrier here, because it sort of catalyzes some local vorticity injection, As these vortices reach the bulk, the effect of it is lost, and it just sort of develops as you'd expect it normally to. But we'll look at what happens to the total vortex line length in the next few slides. The next thing we looked at was the effect of a remnant vortex. So in these experiments, the way you get your condensate is that you start with a thermal fluid and you cool it down so that you get the condensate. And so on the way to doing this, the rate at which you do it, you can actually have some vortices left over from the Kibble-Zurich mechanism that live within your cylinder, and they might live there a long time, and then you might run an experiment not knowing they're there. So we wanted to check again, could experiments tell if one was there or not, based on the dynamics that happen with or without one there. So we made sort of the idealized case where we put a positive sign vortex, so the same as the direction we're rotating in the center, and for an anti-vortex in the center going the other way. And so you'll see for the positive vortex, because it induces some flow in the field, this actually goes in the same way and reduces the relative difference in flow between the potential and the fluid, leading to sort of a slower injection of vorticity into the system and overall a bit less vorticity. Whereas on the other hand, if you have this negative vortex here, this produces some counterflow. And this counterflow allows a much greater injection of vorticity at start times until these vortices move into the bulk. These little flashes of blue you see where sort of the vortex turns over and becomes some anti-vortex for a second. But if you just go to the early time bit again, you'll see that that middle vortex dissipates as the red vortices reach it into little vortex rings, which then decay on their own, sort of removing it from the system until you just have the same sign vortices that live in there and generate the vortex lights we were looking for. So if we look at these effects in terms of vortex line length, you can see that for the general case, this default case, is the same ones we saw earlier. But when you add the protuberance, you see that the vorticity gets added a bit sooner on. And this actually leads to a stronger, more strongly rotating fluid with the more vortices in it at the end. With the remnant negative vortex, again, you also have this counterflow that induces more vorticity at the start, leading to, again, a higher vortex count in the end configuration. And for the positive vortex, you have that flow that sort of goes with the fluid, and you slow down this relative difference between the fluid and the boundary, creating, although the same number of vortices, a slower injection rate of that vorticity into the system. So I'm trying to aim to make this 20 minutes. I think I'm there, but we want to make sure we have time for Theo to talk. But essentially, the main key points of this work were that we showed that even for something as simple as a vortex lattice, how you get there has not really been investigated before. And we find that interactions and reconnection events are vital to actually forming this vortex lattice, and it hasn't really been looked at before. So we think it's quite an important result, and it's great that we were able to simulate it. Yeah, I'm happy to take any questions now if you might have any.
Okay, can I ask the question?
Yeah.
You considered the disorder on the surface.
Yes, exactly.
What about on the surface of container? What about the bulk disorder? Because this is also very interesting, how the vortex glass is formed. Because if they are pinned, they can form different configurations, which is very different from the just conventional vortex lattice. And one can have the vortex glass or some other different configurations. Can you do that?
A vortex glass? I'm sorry, I missed what you originally said.
If you have the disorder in the bulk, not on the surface.
Okay, so you're saying if you have some sort of localized Gaussian or something.
Like we have in our aerogels in Helium-3.
This is like the dirty boson problem, right? You're saying where you have some sort of disordered potential in the bulk?
Yes, yes, right.
And how could we include this within this model? Is that what you're asking?
I think it would be good if you can do that, because it will show to you different configurations which can be formed.
Yeah, exactly.
Different types of glasses.
Yeah. No, yeah, it's definitely something that can be easily quite looked at with this model, but it's not something we considered in this work here.
Okay, thanks.
any other questions to Nick before we move? I had a question about, again, sort of experimentally. Oh, well, I'll ask mine very quickly. There are a couple of hands, but I'll take chair's prerogative. It was just about whether it would be easy to tilt the system as well. So I guess if it's an experiment, you're always going to have some slight offset between the angle of the cylinder and the angle of rotation. And even for a small angle, that breaking the symmetry might lead to interesting effects. So I wonder if it was easy to do something like that in your setup.
Yeah, that'd definitely be possible to do. Another thing you could also think of is if you did this for sort of a dipolar gas, and you have them phase up on like the off axis and sort of rotate that way while rotating along the axial confinement that way. If you can find some equilibrium solution in between where the vortices are sort of torn between lining up due to rotation and lining up due to the dipolar effects. But yeah, in principle, you could add the offset, and I imagine you'd have to rethink the top and bottom plates because they might get caught in the contour between where you have this rough edge surface where it meets the top plate if that was smooth. But otherwise, yeah.
So I'll go with David. I don't know if his hand appeared, but anyway, at the top of my screen first, and then Samuli.
Well, thank you, Nick, for the talk, and yeah, really excellent work. I imagine that the simulations are also long to run, so it's really messy. I don't really have a question. It's more a comment. So by looking at your result, it just reminded me that I've seen something well similar that was done maybe 5 or 10 years ago by Risto Hänninen with the Biot-Savart model. So I think that they were studying the formation of vortex lattices in a cylinder using this model, and they were looking at how the vortex lattice form while you cool down. So when you go through the transition, let's say by moving the transition, let's say from the up to the cylinder down to the cylinder. And so I just wonder if you're aware of those results, and you compared maybe some of those simulation done with the Biot-Savart model with some of yours, for example, for the line density or something like that.
No, I haven't seen that or compared my results to it, but it's quite interesting. So usually my work involves the SPGP, so I look at things like quenches and stuff. So it's definitely something you could apply perhaps with the SPGP, where you look at sort of you quench through in the presence of a rotation.
Exactly. Yeah.
The vortex that forms. But no, I wasn't aware of the work on the Biot-Savart model. I haven't compared that, but that would be interesting.
Okay, thank you.
So Samuli, and then.
Yes, thanks. I might briefly continue on the on the previous comments. So I think Risto did various different simulations, including ones where the cylinder has smooth walls but a rough bottom, and then you start spinning it and you see how the vortex lattice forms. This was related to some experiments done with a rotating fridge in Helsinki. So that should be possible to find, and if you can't find them, just send me an email. I'll show you. And there was another comment which I wanted to make, about the this basically related to what Grisha was saying about this bulk anisotropy, because that is related to experiments which we did in Helsinki in superhelium 3 placed within an aerogel. And so there were some preliminary results where, for example, it seemed like in this aerogel where vortices are strongly pinned by the aerogel right after the superfluid transition, so the configuration freezes immediately. What we got was that the Keeble-Zurek vortices and then vortices created by a drive, so rotation, where it didn't seem to be talking to one another at all. Which seems kind of perpendicular to what you find in this like non-anisotropic system. So from this point of view, I think it would be very interesting to expand the simulation also in that direction.
Yeah, I mean, that's interesting that they don't interact, but I assume maybe the pinnings are just a bit too strong. It can't grab onto the other vortices in that case. But that's something could perhaps add to the model, but it confuses me that they wouldn't interact.
Yeah, well, I mean, I'm not saying we understand that very well yet, but this is certainly an experimental observation.
Okay.
All right, thanks.
Thank you.
May I ask a question?
Yeah, I'm conscious of time, so is it quick? If it's a quick one, we can have one more.
May I ask a question, please? Can you hear me?
Yes, so yeah, go for it, Peter.
Okay, thank you for nice talk. I I did not catch it from the beginning, but I have a question. Your talk probably was about vortices in helium-4, I believe. What would be a difference if you would calculate vortices in helium-3 and helium-4 from point of view of coherent lengths?
Well, actually, so we use the GPE model in this in these numerical simulations, right? And applying that to superfluid helium is a bit of a stretch as it is, because in the superfluid helium, you have sort of these stronger interactions between the fluid. But the main thing we were sort of searching for is the dynamics that happen between the quiescent fluid and the rotating one. And so at that point, the GPE sort of captures the dynamics we're looking for on the length scales that we're looking for. In superfluid helium, right, you have much bigger boxes and much smaller vortices than you'd expect to generate the GPE. Yeah. But because of sort of the mesoscopic dynamics in between the nucleation event and the vortex lattice event, in looking there, the GPE can be applied to superfluid helium, but no, I couldn't say with clarity what would happen between superfluid helium-3 and 4 for this simulation. But it's an interesting question.
Thank you very much.
Thank you.
Cheers.
Okay, we'll end that one there. And if you can stop sharing your screen, Nick,
oh, thank you.
And then we'll try a seamless transition.
So, hi, can you all hear me? Just to check my microphone's working. Good. Right.
I think there was still one question. I was just going to say that that we are perfectly happy to continue the discussion after the second talk, if you're still here, to ask any further questions.
Okay. In which case I'll start. So thank you, Nick, for an interesting talk. And I'm Theo Noble, and I'm going to be talking about catching quantum tornadoes in superfluid helium-4 and using nanoresonators. So I'd like to thank the organisers for giving me a chance to talk, and I would also like to thank my co-authors, particularly Andy Guthrie, now at Aalto University, who did much of the experimental legwork along with myself. And I would also like to thank the team from Moscow for building the nanoresonators used in this experimental work. So first of all, I'm going to introduce you all to quantum turbulence real quickly to make sure we're all on the same page. So this is what you're seeing here is like a little result of a simulation of quantum turbulence. So quite similar to the stuff that Nick was just showing us. And you can see here like the many vortex rings and vortex lines interacting with each other. And the reason we're interested in studying quantum turbulence is that we lack a large-scale theory for classical turbulence. So there's a quote which is probably given to Werner Heisenberg, which I rather like. When I meet God, I'm going to ask him two questions: why relativity and why turbulence? I really believe he'll have an answer for the first. And that really gets to the nut of the issue, that we don't really have a good theory for classical turbulence. And hopefully by looking at this quantum world, we will get some inkling of an idea that can inform our classical world that we live in. So just to illustrate the length scales we're dealing with here, I've included a little image of possibly one of the better known vortices in the universe, which is the Great Red Spot of Jupiter. And you can see that they're spinning happily away and the turbulence behind it as it moves through the clouds of Jupiter. And the length scales here are truly astronomical. The Great Red Spot itself a few times the size of the Earth. And you can also see many smaller vortices, which are getting much smaller and smaller as you look behind it. And if we were to zoom in, you'd see a much smaller vortices. And this is what forms up turbulence. These interactions of many, many vortices at many different sizes, all interacting with each other in a chaotic dance. Thankfully, in the quantum mechanical world, however, we have a somewhat conceptually simpler problem where the vortex lines are fixed in size and are string-like in existence. So conceptually, it's much easier to think about. And this is why we're interested. And we find these things in superfluids, and possibly the first discovered superfluid was helium-4, and we'll be sitting at 10 millikelvin later in the experiments. But what we need to now appreciate for now in the superfluid phase, in the helium-2 phase, is that the superfluid has a single macroscopic wave function going throughout the fluid. So in helium-1 normal fluid, you can imagine all the particles running about all over the place, something like a playground full of children. While in helium-2, you've got more of a marching band where they're all moving almost in unison. So we'll just quickly derive a quantum vortex, like going through the method gone through by Onsega and Feynman, where you just simply take the circulation around a closed loop, and include in your closed loop the vortex. And we can find the velocity from the wave function of the superfluid. And the key insight here is to realize that the phase of the wave function can only change by units of 2 pi as you're going around this closed loop. So that then gives us the quantum, which is equal to Planck's constant divided by the mass of the superfluid particle, in this case helium-4 atom. And it turns out you don't have to worry about multiple quantum vortices, because a 2 quantum vortex would energetically decay into 2 lower energy n=1 quantum vortices, which is quite nice. From here, you can then find that a quantum vortex has a fixed size just by using Landau's velocity. So the velocity where the superfluid breaks down, which in helium-4 is about 50 meters per second. And this gives you a vortex core size of about 0.3 nanometers. And this leads to a topological defect in the superfluid wave function, which means that the superfluid must either end, which means the vortex must either end at a wall or end in itself, forming a vortex ring. So that's what makes up quantum turbulence. And how do we probe quantum turbulence? Well, there's quite a few experiments, and you can also do simulations, as we've already seen. In visualizations, you can use helium ions or hydrogen ice to track quantum vortices moving through the fluid, which are rather nice to look at. However, what we're using here are oscillators, and the advantage of oscillators is while you lose the ability to see what's going on, you do gain the ability to rather finely track the energy that's flowing in the system. So here I show a picture of a tuning fork, which is one of the things we're going to be using later. And this is one of the oscillators that we've been working with at Lancaster for quite a long while now. So this is what you're seeing here in the central graph is the force velocity graph for the fork. So as we're increasing the driving force going into the fork, and the fork's prongs are resonating faster and faster and faster, we just track the relationship between the two. So initially you can see how the velocity and force have a linear relationship below a critical velocity, and then after this critical velocity, shown in the dotted line, while the critical force, we suddenly swap over to a different regime where the force is proportional to the square of the velocity, and this indicates a turbulent relationship between indicates turbulence has been formed around the fork. So, excuse me. Yeah, and in the classical world, we would not see this. Instead, you would see a gradual transition between the two. So you start with Reynolds number. When Reynolds number is far below 1, you're in a laminar regime, and when it's far above 1, you're turbulent. But when it's equal to 1, you're neither here nor there. You're in the halfway house. In the turbulent world, however, it's like flicking a switch. You're either on or you're off as far as the tuning fork is concerned. And this is pretty similar to a low temperature oscillators in helium. So now we understand that, let's go on to the meat of the work. So here you can see an image of a nanobeam that we use, and our nanobeam, well, computer graphic of our nanobeam, and our nanobeam is 70 micrometers long, 1 micrometer above the substrate, above the silicon substrate, and then it's got a 30 nanometer thickness of silicon nitride, and on top of that there's been deposited of aluminium of a thickness of 100 nanometers, and it's about 200 nanometers wide. It is placed then in superfluid helium-4 about 10 millikelvin at the bottom of a dilution refrigerator, and we use a magnetic field, a 5 Tesla magnetic field, to provide and then an oscillatory current to provide a force to move the nanobeam through the superfluid. Movements then produce their own excitation that we can then pick up on the other side. And the original motivation of this work was simply just to see if we could create quantum turbulence using a nanobeam. So at a much smaller length scale than has been used with tuning forks or indeed some vibrating wires. So we tried to get the force velocity graph, however, we could not see the clear-cut transition, which showed that we were creating turbulence, and it did not appear that we were creating turbulence at all on the nanobeam. Okay, fine. Maybe we can create turbulence using some other method. So what we did instead at this point was we introduced a quartz tuning fork, and we placed that tuning fork 2 millimeters above the nanobeam, and then we started creating turbulence about the fork. So what's happening microscopically about the fork as it's creating turbulence? When it hits that critical velocity, we can imagine those remnant vortex lines on the fork bowing outwards. They start reconnecting with each other at the critical velocity, and then they start forming a turbulent boundary layer about the tuning fork, and then they'll start releasing vortex rings into the bulk fluid, and these will fly off. And hopefully our nanobeam will interact with these things and then start creating turbulence, and something will happen that will be interesting. So in order to do this, we just sat the fork creating turbulence at sufficient velocity to do that, and then we just listened to the nanobeam. So we just sat a local amplifier on the resonance of the nanobeam, and we just were waiting to see the resonance change. And this is what we saw. So these are 3 separate time traces taken at different frequencies across the nanobeam's resonance. And you can see like something is happening. However, there's no longer like a clear-cut transition that we're seeing like with the fork. Instead, it's very quick transitions, and it appears that the resonance of the nanobeam is suddenly jumping. And it is a little bit hard to tell really what's going on. And this is the point when really I came into the story. I just finished my PhD thesis at this point, and I looked over my colleague Andy's shoulder, and I saw these measurements, and then I asked him, why don't we try using multi-frequency lock-in amplifier to see what's going on with the resonance in the nanobeam? So this was an instrument that I'd used in the course of my PhD, so I was quite familiar with it. And the advantage of this instrument is that it works at 42 frequencies, not just a single frequency that we were using before. And what we can do is we can demodulate the tone which is on the nanobeam's resonance, and we can send that off to an oscilloscope. And then we simply wait for the oscilloscope to detect a fall in the nanobeam's resonance, and then that will trigger a measurement by the multi-frequency lock-in amplifier, which then sends the data to a PC. And you get something which looks a little bit like this. So you can see the central resonance of the nanobeam there in dark blue, and you can see the background response away from the nanobeam's response in green and yellow at higher and lower frequencies. Now, the restriction with using multi-frequency techniques is that you are a little bit restricted in terms of the measurement time and the frequency separation. The closer together the frequencies are, the longer you have to measure to be able to distinguish between them. And we found a compromise of measuring for about 2 milliseconds, and then having the frequency tone separated by about 500 hertz. And this was enough to see what was going on. And this is an example of something we saw. So we can see something happens to the nanobeam, and the nanobeam's resonance starts moving upwards. So it appears like appears that maybe a vortex ring from the fork is moving near the nanobeam, or maybe even touching the nanobeam, and is messing around with the resonance a little bit. But doesn't. And then here's another event, and you can see this is much quicker than the last one. It rises up, the resonance rises up quite quickly, and then suddenly falls back down to earth, to the natural state, relaxed state. And this is quite indicative of most of the things we saw. Most of the things we saw, which is very quick blips, stuff like this, where clearly something had moved close by, was just touched, and nothing really came of it. However, occasionally you saw something much more interesting. You saw events like this. And you can see here that instead of just falling straight back down, in this case, we seem to have stabilized some sort of steady state at the top there, about 3 kilohertz above the usual frequency of the nanobeam. So you can see that there's this gradual rise up over the course of about 10 milliseconds or so, and it's stabilized for another 10 milliseconds before very quickly decaying back to the natural frequency of the nanobeam. And you can see another event, this time a little bit clearer. You can see this time the rise time from between the two states is about 6 milliseconds, and this time it's stabilized for much longer, for about 50 or so milliseconds before it decays back to the usual ground state. So at this point, we asked ourselves, what's going on? And in order to answer this, I created a computer program which could find the frequency jump of this plateau. So what we're seeing is that we're seeing this 3 kilohertz jump above the natural state of the nanobeam, and this apparently excited state where it's jumping up by 3 kilohertz. And then you can start measuring for a long, long, long time, and you can bring together many, many events, and you can start building a histogram of these jumps. And this is what we saw. So this is histogram, and first of all, disregard these bottom events here. These are all things where there's been a blip, these blips which I showed earlier, and the program has falsely fired off. We don't need to worry about those. Interestingly, we see some things at 1.5 kilohertz, which seem to be some sort of halfway house from the 3 kilohertz jumps. Remember, those will be mentioning them quite briefly at the end. And then we see the vast majority of these events which have a plateau, they have this 3 kilohertz jump. There's nothing above really 3 kilohertz or 3.1 kilohertz. So there's nothing significant, there's nothing beyond there. There's some sort of cutoff, and it seems to like 3 kilohertz. And what we think is happening is that the nanobeam is essentially catching a vortex. So a vortex ring comes traveling off the fork, it travels through the superfluid helium-4, and eventually comes in such an orientation that it actually is able to lie across the nanobeam, and then it starts interacting with the nanobeam as it is coincident along the nanobeam. And this has precedent. The original experiments that confirmed the circulation quantum performed by Wienen back in the 1960s, I think, engineered such a situation where a vortex was coincident along a vibrating wire in a vibrating wire in a rotating cryostat. And then Wienen exploited the Magnus force of the vortex on the wire to lift the degeneracy of the wire's resonance, and then you could measure the circulation from that. And it appears here this is similar to what is going on here. We're catching a vortex, and it's altering the resonance of our nanobeam. And something to further convince you that this is definitely a vortex event, when the fork is not turbulent, when it's not releasing a vortex rings into the bulk fluid, we're not seeing anything on the nanobeam. So on the left-hand side, you can see the fork velocity, and you see the fork drive force on the x-axis there. So that's essentially the same graph that I was showing you earlier. And on the right-hand side now, we have the rate of events measured at various fork drives. And you can see as we increase the fork drive, we're increasing the rate of events, which is exactly what you would expect. As you increase the rate of events, more energy is going into creating quantum turbulence, and more vortex rings are getting released off into the bulk fluid. and then eventually getting catched by our nanobeam. So it's definitely vorticity. So what happens when the vortex lands on the nanobeam? Well, first of all, of course, there's Magnus force, which I've already briefly mentioned, which is exploited by Wienen. And what happens in this case is that the circulation, the movement of the superfluid about the nanobeam as the beam is moving through the fluid creates a transverse force as compared to the beam's movement. And this will be an extra force created by the vortex. There's another force that we think is also partly responsible, which is the surface interaction. So this is a little bit more complicated, but we can think of the surface, which is 1 micrometer away, as interacting with the vortex itself, because it affects the flow field of the vortex. And one can model this by placing an image vortex beyond the surface. So basically making the surface a mirror in some respects, and placing an anti-vortex at the same distance away from the surface as the original vortex. And then you can plot on top of each other the superposition of the two flow patterns to work out the flow pattern of the whole of the fluid. But from this, you can model the interaction from the surface and this image, the original vortex and the image vortex, as the intervortex force. And this will lead to a static force pulling on the nanobeam. And we think that a combination of the Magnus force and this force is what's responsible for causing that rise in frequency. Both of these forces are going to interact with the nanobeam, and they're probably going to increase the tension of the nanobeam. By increasing the tension, you then naturally increase the resonant frequency on the nanobeam, and that leads to that 3 gigahertz jump that we're consistently seeing. In our own modeling, we've been able to get about 1 gigahertz jump. Our own model is, quite naive. We don't include many of the intricacies of the system for the fact that the nanobeam, we assume that the nanobeam is a perfectly has uniform density, which it does not. It's a composite beam, aluminium on silicon nitride, and we also assume the nanobeam is very nicely smooth. It's almost definitely not. It's going to have rough edges, etc. There's many intricacies we don't factor in. So we're quite happy in being on the same order of magnitude in our calculations, but this is something further work could go into. So what else can we look at? So, so now we have a really nice explanation of what's going on in these events. So initially we have a vortex-free state. There's no vortex along the nanobeam. And then in the plateau, we have a vortex along the nanobeam. And that's interaction with the nanobeam and increasing the nanobeam's frequency, as we've already discussed. Now, in between these two states, there's 2 other processes, and these 2 processes we do not have such a good idea on. But we can hazard some guesses at what's going on. So in the trapping, so when the vortex is landing on the nanobeam and starting to raise the frequency, we think what's happening is the vortex might be creeping along the nanobeam, as illustrated in this top figure here. You can kind of see the what we think is happening, and it will be creeping along the nanobeam before eventually stabilizing at the plateau. The end process, we think what happens is that it's a different process. We know it's a different process because it's a lot quicker than the rise time, and it's so quick, in fact, that we don't see it in the time resolution we've got, so it's a lot quicker than 2 milliseconds. And what we think has happened is that another vortex from the fork, or from the turbulent fork, or maybe the system pulls another vortex nearby, and another vortex comes in, interacts with the vortex on the nanobeam, and essentially reconnects and rips off the original vortex off the nanobeam, and the nanobeam is cleaned in this process and is then vortex free and goes back to the normal state, its normal resonance. So this is our explanation of what's going on. From this, we can do some other things as well. So we can start looking at the wait time in between events as well. So this is the how long between vortex interactions on the nanobeam, and we could measure this at different fork velocities. And what you can see is what you would expect, that as the fork velocity increases from 74 millimeters per second there to 90 millimeters per second, is that you can see the wait time between events significantly decreases. So at the lower speed, we have wait times in the order of 1,000 seconds, while at the fastest speeds, you are waiting 20 milliseconds, no, 20 seconds even between events. And this is exactly what you expect. As you're increasing the energy, you go into the quantum turbulent tangle, more vortices are getting released off into the bulk. And this is what we're seeing on the nanobeam. So this suggests we've got a great probe, independent probe to the tuning fork at what's going on in the vicinity of the tuning fork. Another thing we can look at is look at the event time, the lifetime even of the vortices on the nanobeam. So the time from the capture of the nanobeam to the release, capture of the vortex to the release of the vortex from by the nanobeam. And what you can see here is that it's not affected by the tuning fork's velocity, which is slightly counterintuitive to what you might naively expect, simply because you would expect if there's more vortices about, then surely there'll be more chance for the nanobeam to interact with another vortex when it's got a vortex on it. But that apparently is not the case. So it seems that we're looking at some possibly probing something different here. We're not probing the vortex tangle about the fork here. Maybe we're just probing the vortex density nearby the nanobeam, and maybe that's not really strongly affected by the turbulence on around the fork. But this is something which further work can really go and start looking into. So where do we go from here? Well, a simple thing we could do is just simply adjust the surface height of the substrate above and below the nanobeam, below the nanobeam, and just simply confirm that that surface force that I was talking about is really the culprit. We think that is probably the main culprit as opposed to the Magnus force, simply due to there isn't really a the nanobeam isn't degenerate. It doesn't have the nice degeneracy that we had with Vinden's wires, and the resonance in the other mode compared to the mode we're exciting in is at a significantly different frequency. So we expect the Magnus force not to be a big culprit. Other things we can do is we can, if you remember those 1.5 kilohertz events that I was talking about earlier, where it had a plateau at 1.5 kilohertz above the normal state, we think this is a situation where you have a vortex half on and half off the beam. Now, presumably, it'll be possible to excite Kelvin waves on these vortices on the free end of the vortex in similar experiments to Zaiv. And then hopefully you could study the energy flow of these Kelvin waves on interacting with the nanobeam. And this is quite interesting for quantum turbulence research, where Kelvin waves are quite important. And another thing we could do is we could presumably build a camera of multiple beams, nanobeams really close together, and then build up a real picture of how vortex rings fly off a quartz tuning fork or another oscillator device. So I think that's about all I've got to say, and that's pretty much exactly on time. So I'd like to thank you all for listening, and I'd like to thank the other members of the Lancaster Ultra-Low Temperature Group, as well as Andrei Golov, Oleg Kolosov, Peter McClintock, and Vinden for helpful discussions as we were discussing the theory of what was going on with these nanobeams. And I would also especially like to thank the EPSRC and the European Microkelvin Programme for funding this research. Thank you all for listening, and I'll start taking questions now.
Great, thanks very much, Theo, for an interesting talk, and to Nick for two really interesting talks today. So first of all, we can take questions on Theo's talk, and then it can just be opened up for a wider discussion. I may have to vanish to go and fetch my daughter from childcare, but I'm sure Zoom will just keep ticking. So any questions to Theo first? David Day, is someone that I see with their hand up?
Hi, yeah, thank you for the really interesting talk. I have a really stupid question. So when one of the vortex is trapped into your beam, well, you've sketched that the vortex is basically there trapped, but how does it close out of the beam? Does it form a ring?
So yeah, that's a good question. I'm not 100. I think if we were to form a ring, then it would, the ring would probably try and collapse on itself. I wouldn't be 100% sure. So I think what I wasn't showing in the sketch was that it ends like in the walls of the, there's two walls for the nanobeam, which the nanobeam sit in. So it might end at those walls.
Yeah,
which is
okay.
why would happen.
I understood. Thank you. Yeah, very interesting.
Thank you. Thanks. Any other questions?
I just have a quick comment, if that's okay.
Yeah, sure.
Yeah, so actually your picture of your vortex line along your nanobeam is very reminiscent to me of some work by Rina Ziev at UC
I'm familiar.
Davis. You know these ones?
Yes, it's very similar.
Yeah, it looks very similar the way you have it lying along the beam and then peeling off. Just in case you hadn't seen that work.
Yeah, we were looking at our work when we were going through this, looking for explanations of what we were seeing.
Thanks.
Yeah, thanks.
Way.
Oh, and very nice talk, Theo. I wanted to ask you whether it's possible to vibrate your nanobeam vertically.
Not in our current setup. So if we wanted to do that, then we would have to rotate the cell, which I presume would probably be possible if we wanted to re-engineer things and then see what was going on. Yeah, this is something we've thought about ourselves as well. See how this would change things.
Okay, because if you can, then you probably would be able to see, the vortices peeling off from your beam.
Yeah. Oh,
that would be interesting.
Yeah, that would be interesting. Yeah.
Okay.
Thank you.
Yuri.
Yeah, hi there. Looks like Lancaster has now two projects for the vortex camera.
Yeah.
Right. Well, if you sort of compare them, compare the resolution that could be achieved. One for this quasi-particle camera in Helium-3 experiment, and another one, the camera that you're proposing for Helium-4 measurements. So what kind of resolution can be achieved in both cases?
So the question really is, what is the length scale of the oscillators you use? So with the quasi-particle camera, we use quartz tuning forks, which are much bigger scales. And then ideally, if some sort of future camera in that development, you want to go to the nanoscale as well. So then you could start packing these things closer together. So the quasi-particle camera, has a resolution of 25 pixels, which is good. It's really good, and it's quite an impressive experiment. But you wouldn't really go to Apple and say this is a this is a really good camera for future phones. So yeah, you really want to pack in these pixels a lot closer together, and using nano devices, you'll be able to pack it a lot closer together. And in Helium-3, the advantage then would be that because the length scales are bigger with the coherence length and the with the vortex sizes as well, is that hopefully you'd be able to see things easier.
Mm-hmm.
Does that answer your question?
Yes, indeed. Yeah, just a small one. That's in this setup, in the one you were talking about, if you sort of build this camera and put your nanobeams very close together, I expect that you totally distort the picture. The interference between them will be quite high. Is it right?
Yeah. So it depends on how you do the multiplexing. So you'd have to try and make sure that your nanobeams aren't too close together in frequency, and that also you'd be able to tell which one was which. And if they were too close together in frequency, then yes, you're correct. Then they'll start interfering with each other, and then then you'd have a problem. So you're right. Yeah, you'd have to engineer your experiment carefully.
All right. Thank you.
No problem. Thank you very much.
Anyone else? Where you've still got your hand up, but I don't know if it's just a remnant hand.
So Wei has remnant.
Still attached. I didn't realize if I chopped someone off from asking a question about Nick's talk, if they're still here. And
Hello?
yep.
Well, Andrew, I have a question to Nick. Can I raise?
Yeah, go for it.
Yeah, it's just a quick question. I wonder whether Nick ever calculated the torque profile in the BEC.
No, I didn't. But yes, this is something you could do. I've seen some code that does that, but I've not applied it. I only saw the code that worked in a 2D environment, so I've not developed any calculation of torque in this 3D landscape. But no, you're right. That could be interesting to look at.
Yeah, I wanted to know how fast the angular momentum is injected and what affects this rate. And furthermore, I guess you can easily rotate your container faster, say speed up or slow down, and then see how this rate of angular momentum injection changes. I wanted to know what really controls it.
No, you're right. That's definitely something you could look at. You are limited in a GPE from rotating too quickly. Eventually, sort of the centrifugal effects sort of take over, and you just end up with some giant macroscopic, multiply quantized vortex in the middle instead of the vortex lattice you're looking for. So you're limited in sort of how quick you can go with it, and you're limited in how slow you can go with it to the point where you won't inject any vorticity at all because you don't break the critical rotational velocity. But no, yeah, the injection of sort of torque as a study of roughness or the rotation rate would be interesting to look at, yeah.
Okay, thanks.
Peter.
Yes, thank you. Thank you for a nice talk. I have a question to Theo. It's a naive question. If I got it correctly, when your nanobeam interacts with the vortices, its frequency is going to rise. Why is that?
Yeah, so because you're having the effects of, well, the Magnus force and this surface interaction, this increases so basically you can think of the surface interaction as a static force pulling down on the nanobeam towards the surface. This increases the tension in the nanobeam, and then that increases the frequency of the nanobeam system.
Okay, thank you. That's okay.
Yeah, thank you.
Anybody else? Well, if not, just to say our next talk is in 2 weeks' time. That's 6th of April, and it's Dr. Igor Todoshenko from Altva University, who's going to be talking about mobile solid helium-3 on carbon nanotubes promoted by topological frustration.